I was basically the last time I did this, I was about to. I was kind of comparing so the math solutions, the math in the solution for 1.1 still. Oh, the actual title is wrong. Let me see if I can change that. 1.1. There you go. I'll update the titles as well later for the other videos. And basically, if I remember well, I think I'm gonna just close. I just wanted to today close out with trying to understand where the whole thing with the current was taken, because that's what's bothering me a bit more. But I think I finally figured out what how did I get the second part here, and I came across these while watching some videos on the sort of the inner product and stuff like that, and then I realized that, well, yeah, that is obviously because what was going on here, right, is in C, where you're assuming the two regions are actually overlapped, and so this doesn't hold true anymore, and essentially I don't know if you remember that. You can go check that in previous videos, but like essentially the way that I got to that solution was, I mean, at least the first part was solved, right? But then I kind of had two components of it. So one was like these times that, I guess, and then I think I had like these times that, something like that, right? And then, well, essentially, like that is actually that is actually the definition of the inner product for complex wave functions. And if I just inner product identities complex numbers, I think that is actually one of the things that you find, right? I don't know. I found this in the video, but like there's that thing where so inner product formula with cosine. There's a yeah, there you go. So the dot product of A and B equals to the length of A times the length of B times the cosine of the angle between them. There you go. And that is actually, this is something I just like, I don't have all these identities in my head, so that's why. Yeah, but that's why it's good to kind of recap the solutions, because like I the way that I developed the exercises, I left it at a point where I think mathematically was correct, but it was, it definitely didn't match that, but that kind of makes sense. So this means, that essentially these in here is like, and these, right, so actually it's like 2 times and then it's like these and then the cosine, and now how these angles are defined, these I don't remember. I have to come back to the videos before, because I didn't sadly save the notes. Maybe I should save. The thing is, I don't like saving the notes, because then I don't find them, I don't understand them, so I'll just have to live with these. But I remember there was a way you're actually kind of redefining this stuff, and then so you were getting these, and now like there's the 2 is missing here, but I think that this 2 was getting cancelled out because I don't know why, but I think that was cancelling. I'm happy with this. I'm happy to know that this is actually probably coming from there, because essentially that's the target of the exercises. You want to, of that specific question, is that you wanted to show that it's periodic. So that's why, like, if you manage to express that as something that has a periodic function like the cosine function, then you're good to go. So I think I'm going to leave it like that. At some point one has to kind of stop. And I spent too much time on this exercise already. But now the whole thing with the density, like this is what I got wrong. And let's take a look at this again, right? So because I don't know where, like, how do they compute it to be like these? So starting with the same initial wave function and assuming that the two eigenfunctions are real and isotropic, take the two partially overlapping regions to be two concentric spheres. Compute the probability current that flows through the first region, which is basically the outer region. Right. So yeah, I have to I reasoned that at a high level, and I remember that the problems I had was like I was making a big assumption in terms of what isotropic means. Now, having read the first exercise of the next section, it's got to do with something like that it doesn't depend on the direction. Of the particle. I don't know. Last time, I mean, I did check what isotropic meant. And I think this was more like it's just the same everywhere, kind of, right? The process proceeds at the same rate regardless of direction. Simple. Okay. It's got to do with something being the same, being equal, right? Regardless of the direction. So it probably means that it's not like a curve or something like that where is one that does not depend on direction. Man, I hate Quora. That doesn't depend on direction, it evaluates to the same value in different directions, all of the things being equal, and it's just a function of only the radial distance from the origin. Interesting. For example, f x y z is x square y square z square only depends on the radial distance from the origin and not on the angle this radius vector makes. Can we plot that? Plot 3D. What is the app called? I think it's Desmos, right? Like, can you just, or I don't know, people, what do people use to just plot some things like on the fly? Desmos 3D plot, maybe. I know this because I know there's an app and you can actually plot stuff. And I want to basically, whoa. How do I clean that up? How do I clean that up? God. And it's in German. How do I type things in here? X squared, no. X. How do I? What? Oh, there's some kind of keyword things here. Okay, so x squared plus y squared. Ugh. Okay, but that's not. That is not a 3D here. I want a 3D. Ah, come on. Make 3D plots online. I don't want to have to download anything. trying to, so what I'm trying to do is I'm trying to visualize this function to understand a bit more. It only depends on the radial distance from the origin and not on the angle this radius vector makes with any other Cartesian planes. That's gonna go slow. Plus, and then do I want to make it plus Z undefined symbol? Oh crap, I mean that is 4-dimensional actually, isn't it? What am I trying to do? Of course, I need 4 dimensions for that. Good luck plotting that. Good luck plotting that. Okay, 0, 1 is... Yeah, anyway. It does not depend on the direction. It evaluates to the same value in different directions. What does it mean direction in this case, right? All other things being equal, and is this a function of only the radial distance from the origin? So what this means is that, like, maybe let's try to think in 2D. Maybe I'm just overthinking that, right? But let's try to think in 2D, or even just 1D, right? Which would then, the one input parameter. For one input parameter, what we're saying is, kind of that the function only depends on the distance of the input to the origin, right? But that's okay. That means, I mean, isn't that like the case for it's like any function in this case when we're talking about just one input? Because, well, like the value is going to depend on that, so it just can be here, can be there, can be there, so it can be whatever, right? Probably what it means in this case is that it's going to be symmetric, right? Because the distance to the origin is the same for this point and this point. Let's say this is +1, this is -1, so that's what it means in that specific case. Okay, and in the case of like a two dimensions or 2 inputs, so you know you need like 3 dimensions for that. It means that like for the, say, for all the points that are like at the same, so bad, like the same distance to the origin, it's going to be the same value. The same Z value. And so, you know, that kind of means that it's going to be like a, it's like a, something that has like a, it's like a cone or something. Not a cone, but like something that just, whatever it is, but it kind of has a shape. Okay, yeah, whatever it is, right? But it's like, it doesn't matter in what direction, whatever that means, I don't know. That always has definitely a an impact on the exercise itself, right? But anyway, where was I? So I was here. So it says start the same initial wave function, assuming that the 2 eigenfunctions are real and isotropic. Then take the 2 partially overlapping regions to be 2 concentric spheres of these. That's interesting, because now the whole thing with concentric, it makes sense in a way, right? So because before I was a bit like, I was not really relying on the fact that this was concentric in any way, and maybe just if I assume I'm 3D space or in just 2D space, and then these are just two concentric spheres, right? This means that actually, as we approach, if this is, let's say, let's fix that as the origin, right? The center of both spheres, of both regions. I'm taking a look at it from the top. So the eigenfunctions are isotropic and real. So this means that they all kind of get the same value. It doesn't matter what you look at, because, so let's say if you're at the edge of this area, it's the same radius to the center. So they're all going to get the same value. And then this is going to change gradually. As you approach this circle here. Okay. Probably current flow, and that, okay, so and this is what was complicated, because I just couldn't find a formula for these. I just would find a lot of things, right? But not something that it says it can easily be computed to be like that, but that doesn't mean it's a starting point. Obviously, it just, I don't know what is the starting point to get something like this. Because let's just think about these. Like, if you, the current is, how is the probability density changing, right? And so here you're gonna have like, here you're gonna have, let's say this is the one circle, this is the other circle, right? And here you're gonna have like some values of this density function, right? It's going to be just, because I think the mistake I was making by then is that I was saying, oh no, it's isotropic, it means it's the same, but it's not the same. What it means is like, this actually can have any shape. I'm really badly at drawing this, but like, let's say this is this point, and like, let's say, you know, this is like, we don't know what these eigenfunctions look like. I mean, but there can be any kind of thing from here to here or something, right? In terms of the value, how's it? It's just that it's the same shape all around these things. Now I understand this better, right? So this is kind of the elevated shape of version 1. And here you have the concentric one, right? But of course here, I'm just overlapping them, but here you would kind of have the highest probability, because you would be adding them, right? If you think about the probability of finding the particle there, because it's in a clean superposition, right? It's like that. So that's basically well, unless you actually have to take this result, right? No, of course, not this, yeah, actually, yes, you probably can take this result, because it says here, now that they all overlap partially, right? Which is a subcase of overlapping totally. So I would actually have to take that result and say that's a probability density. How would we even go about applying these? I see here now where the R comes from. That's the radius, right? That makes sense. But like the current density formula, quantum mechanics, current. I think that's the mistake that I was making. I took a really simple approach to these, where I was just looking at it as like, well, you know, I have the probability density of of one wave function, I have the probability density of the other wave function, and so I have to calculate, but it makes no sense. You have to take a look at the sort of a combination, right? So this is the wave, this is the probability density when there's an overlap. So actually I have to take that, I can take that result and then just work with these. And now this makes more sense because all the definitions that I was finding here are all defined for just one wave function, right? It's just that we know these two regions have this specific overlapping property. Give me a second. I think I need it outside. Give me a second. Back there again. So current density. Current density. Not current density, current flow. Probability density. Oh god. Probability current that flows. Quantum mechanics. It's good because like doing these exercises helps at least to get the mechanics of like what is it that you have to, you know, what are the starting points, what is the reasoning the reasoning you have to follow to solve to answer specific questions, right? Look at these word in German, Wahrscheinlichkeitsstromdichte. Awesome. Probability current. Definition. Okay, so here actually there's different different formulas, but there you go. Okay. In non-relativistic quantum mechanics, the probability current J of a wave function psi of a particle of mass m in one dimension is defined as. And this is where my, I think, original reasoning went totally wrong, because I was like, well, I was saying, I now remember, I was reasoning, I was just saying, you know, if they are isotropic, then the derivative makes no sense. Like there's no gradient, which is not what isotropic means, obviously. Now that I have figured what isotropic really means, then of course these derivatives make sense. And it also makes sense that there is a sinus in here in the solution. Yeah, because obviously the that's the starting point. It's a cosinus here, right? So but let's go back to these. So it says it's h bar divided by 2mi. I guess they dropped the I because what? Because there is oh no, look at these. Okay, what? Yeah. Then there's a complex conjugate of a function in the real part. Okay, so the imaginary part. No, the probability current is proportional to a Wronskian, whatever that is. In mathematics, the Wronskian is a determinant introduced by Joseph von Wronski and named after him. It is used in the study of differential equations, where it can sometimes show linear independence in a set of solutions, whatever. In 3 dimensions, okay, so we are probably looking at the 3 dimensions case, I don't know. It generalizes to these, where h bar is the reduced Planck constant, m is the particle's mass, psi is the wave function, this is a delta, the gradient operator. This can be simplified in terms of the kinetic momentum operator. What the heck does that mean, like, to actually have the delta here in the end? God. Here they just put the R in there, as if they were just like taking it from here. Like, I mean, this is the, whatever this P is. These definitions use the position basis, but momentum space is possible. Connection with classical mechanics. Motivation. The definition of probability current in Schrödinger's equation can be used to derive the continuity equation. Is an equation that describes the transport of some quantity. It is particularly simple and powerful when applied to a conserved quantity, but it can be generalized to apply to extensive quantity, which is exactly the same form as those in generalized electromagnetism. Continuity equation. Woohoo! Nice. Then the divergence theorem implies the continuity equation according to the integral equation. Continuity equation. Why is this important? Continuity equation. Quantum. What is quantum continuity? The second term, the equation for quantum is the second term is on the rate at which probability is flowing out of volume V. Altogether, the equation states that the time derivative of the probability of the particle being measured V is equal to the rate at which probability flows into V. The time derivative of the probability of the particle being measured in V is equal to the rate at which probability flows into V. In quantum mechanics, it's conservation of probability. The terms of the equation require the following definitions and are slightly less obvious than other examples above, so they're outlined here. Okay, so maybe this is so the wave function psi for a single particle in position space, that is a function of position r and time t. The probability density function is this. The probability of finding the particle within V, the volume at T, is denoted by the integral within this volume of that probability function. I know that. That's okay. That's correct. And then the probability current, aka probability flux, is this. With these definitions, the continuity equation reads. That bothers me because I have no idea how to read that. Like I will definitely stick to that more because I'll stay in this exercise more because I just want to understand that. I mean, either form may be quoted. Intuitively, the above quantities indicate this represents the flow of probability. The chance of finding the particle at some position r at time t flows like a fluid. Hence, the term probability current, a vector field. The particle does not flow deterministically in this vector field. Okay, so I think what this is saying, is that it's just a way to show that that the probability density function is smooth, right? So that you don't kind of like it's integrable, right? Like, so you don't have something like it goes like this and then suddenly there's just a break and then it's like that, right? Because then you can't, you must be able to integrate that probability density function to, like, for this to be 1, right? The probability current flux it's like I want to understand where is this coming from, because that bothers me a lot. I don't want to just kind of know that I have like and that's why I'm definitely going to spend more time into this. I want to understand what is this really telling me. And maybe I should just step into more of a classical setup first to try to understand, why things look like that. Continue the equation. But I think that's what it means, right? We generate one equation by multiplying the Schrödinger. So we generate one equation by multiplying the Schrödinger equation with the transpose, where it's conjugate complex. The conjugate complex, complex conjugate. We generate another equation by multiplying the Schrödinger equation with minus this and add both equations. The result is, why the fuck do we do these? This can be in the form of a continuity equation. You should check that beside the probability density, also the probability current density, both are real quantities. This equation is a one-dimensional version of the continuity equation that appears in different areas of physics, such as fluid dynamics or wave theory. We know that for simplicity, up to here, we have only dealt with the one-dimensional version of Schrödinger equation, which yields the one-dimensional version of continuity equation. So we integrate this equation from minus infinity to plus infinity and vanishes at infinity, which is plausible. So the probability should be 0 at points of space that are inaccessible to the particles, for example, infinity. So okay, the statistical interpretation of this is one of the central axioms of quantum mechanics. Getting there somehow, but so how to make sense of that? Maybe I have to step into other areas where this is defined. Continuity equations are a stronger local form of conservation laws. For example, a weak version of the law of conservation energy states that energy can neither be created nor destroyed, and the total amount of energy in the universe is fixed. This statement does not rule out the possibility that a quantity of energy could disappear from one point and okay. Yeah, I get it. That's the point of these. So this is just a math way to just say, like, the conservation of energy is locally smooth, right? So you can't just, like, of course it's a zero-sum game, but like you can't just like suddenly there's a bunch of energy disappearing here and then appearing there, right? There's going to be a smooth transition, and it's the same with probabilities, I guess. When you have like a wave function, it's like the probability of finding the particle somewhere, there's just a smooth transition. It just can't be like that's what this is saying. It's locally conserved. Yeah, it cannot teleport, so to say. Okay, this makes sense. But now, how do we define that? It's defined when the flux can be defined. To define flux, first there must be a quantity Q which can flow or move, such as mass, energy, electric charge, whatever. Number of molecules, the volume density of this quantity. Rho, that is the amount of Q per unit volume. Volume density, the amount of Q per unit volume. The way that this is that this quantity Q is flowing is described by flux. The flux is a vector field, which we denote as J. It isn't some examples of properties of flux. The dimension of flux is the amount of Q flowing per unit time through a unit area. For example, in the mass continuity equation for flowing water, if 1 gram per second of water is flowing through a pipe with a cross-sectional area of 1 square centimeter, then the average flux inside the pipe is 1 gram per second per square centimeter. And its direction is along the pipe and the direction that the water is flowing. Outside the pipe, there is no water. The flux is 0. So if there's a velocity field, U, which describes the relevant flow, in other words, if all of the quantity Q at the point X is moving with velocity Ux, all the quantity point X is, okay, so the velocity is uniform at a specific point, I guess, or then the flux by definition is equal to the density times the velocity field. For example, if in the mass velocity at each point and there's a water density at the point, mass. Okay. In a well-known example, the flux of electric charge is electric current density. So you need to understand, of course, how much of something there is in that something, in that volume, and then at what speed this thing is traveling. Speed understood as a vector, right? And then that's what defines the flux in the most simple uniform kind of case. So if we think about probabilities, like you have to think about how much probability there is in that section, in that volume, and then what is the speed, right? That's why you do a derivative, I guess, because you want to know how is that flowing, how's the probability flowing, is it getting slower as you increase your position, for example. Okay, that's why there's these derivatives in the that's why there's these derivatives in the function somewhere, right? Quantum mechanics. Let's continue the equation. I want to know probability current. Quantum mechanics. That's why you have these in the first place. I don't know. I have no idea where that comes from, though. The mass and everything, I guess. Why there's a minus, though? In a well-known example, the flux of electric charge, if there's an imaginary surface S, then the surface integral of flux over S is equal to the amount of Q that is passing through the surface S per unit time. Okay, so if we think about like the complex plane, and we actually have a bit of a kind of a surface, the rate at which Q is flowing through the surface S is a surface integral. Awesome. What is a surface integral? Is the integral on the surface, I guess? Like just kind of below? Is it that the double? Is this the cool? I guess I'm gonna be leaving it here. I'm getting definitely too deep into this, but I like it. So there's a surface integral. So yeah, you want to calculate the volume probably under these, right? Probably. And then flux density. Okay. The integral form of the continuity equation states that the amount of Q in the region increases when additional Q flows inward through the surface of the region and decreases when it flows outward. The amount of Q in a region increases when Q is created inside the region and decreases when it is destroyed. Apart from these two processes, no other way the amount of Q in the region change. Mathematically, the integral form of the continuous equation expressing the rate of increase of Q within a volume. So this is the surface integral of the closed surface. I think this is just over-formalized. I mean, over-formalized. It's mathematics, right? So it just needs to be formal. But it's essentially, intuitively, it's just, yeah, it's like how, it's basically the amount of probability, like, it's the amount of probability that moves through that specific volume. So I guess, like, the thing is, I still don't understand why is it defined like that, though. The gradient operator. So this is the gradient operator. And where's then P? Oh God, sorry. Gradient operator. Learning a lot of things still just with problem one, man. I've spent like probably 5 hours on this already, on this problem. I'm trying to just make intuitive sense of the formula, right? Kinetic momentum operator. The momentum operator is the operator associated with the linear momentum. The momentum operator is the position representation. An example of a differential operator. For the case of special dimension, the definition is I think I'll need that later because I think the first exercise of the next section does actually need a change of basis, and I think that's what we have to do a derivative and stuff like that. Okay. Let's stick to these though. If we would just stick to these, right, what this is saying is in a non-relativistic quantum mechanics, the probability current J of the wave function psi of a particle of mass m in one dimension is defined like these. So, but I mean, I know we're not in one dimension, but it's like, why do you actually need a minus? That's what I don't understand. So we're okay, so you do. So essentially, right, it's the probability is like the how much of something is flowing through that something, right? So I understand you have to do the derivative because you want to calculate the velocity, and that's what we found, and I don't know if I can get to that explanation. Here, yeah. So there's a quantity Q, which is the probability, and then you multiply that probability by the speed, right? The thing is, the exercise is asking us the problem is I don't see here the whole I don't see here the probability density function anywhere. That's what bothers me. I mean, here you see. That's the first question. Is like why you're doing the derivative of the wave function and not. Okay. I'm looking at the wrong place, right? So this is of course this is just the probability current of the wave function, and what we want to know is the probability current of the current density of the density function, or probability current that flows through. That's what I don't get. Like I don't get why. because if I take, it bothers me, right? Because if we would just be doing, that's what's confusing. If we would just be doing the current of the wave function, then the cosine wouldn't appear. So I'm assuming we need to do the current flux, the probability current of the probability density function, and so of these function, right? Because then we have the cosine, and that's why a sine appears here. I don't know really how you plug in the r in this case, but it's just the radius, right? And I guess you can do that. I guess that's what you can do because, okay, so I guess that's what you can do because you know that they are isotropic, so the values only depend on that radius, right? That's why you can just do. That's why you can get rid of x and then just focus on the actual radius of, like, you know, this eigenfunctions being a function of the radius. What I don't understand is why it still doesn't make sense. No, it still doesn't make sense, you know? It's not like, God, it's just not that either. Like, I don't know where to start. I just don't know what is my starting point. I don't understand why these doesn't include, like, the starting point is not the probability density function, but it seems to be that it's the actual wave function. Maybe because you want to kind of keep the fact that there is a complex part to it, right? I will dig into this a bit more off stream if possible, and then see if I can comment on that a bit more and explore that next time, hopefully in a couple of days, because essentially that's what it's saying. So it's an initial wave function, assuming that two eigenfunctions are real and isotropic. Okay, so it is definitely, like, it is just definitely the wave function. It seems to be the wave function, your starting point, not the actual probability density function. I don't know why though. Compute the probability current that flows through. That flows through that region. I mean, we have a starting point, so maybe that is why. Maybe that is why you have that minus in there. Because no, it's also this makes sense. Cool. I'll be doing some. I'll try to dig a little bit more into these. Think a bit more into these, and try to record at least my, like, sort of in terms of voice notes, because I won't make it to stream again today, but I'll try to stream a bit more often next week. But I wanna, yeah, that's definitely something to dig into. Definitely, the whole probability current. I understand, I think, intuitively what it means and what you're trying to do, right? So you're trying to show that these things are just continuous, like that there's no. What does the solution say? The solution say blah 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 blah, and vanishes are since one or the other eigenfunction vanishes at that point. This can be seen through the continuity equation in the following alternative way. Oh God. Whatever. It's like, this is super abstract, right, notation wise, but like there's just some nice simple intuition that one can build from that. It's really complicated to unpack, and now I understand. Yeah, there is the S, and this is the surface, right? So that's the surface integral on this region, I guess. And yeah, learning new things every day, that's always good. See you next time.